All right, so first of all, I'm very grateful to the organizers for the opportunity to give this talk, which is going to be on LSS probes of cosmic acceleration. In particular, I talk about the phenomenological approach to screening and the setup. And this is work done with Zvonimir Vlad. It's a series of work. You can find them online. So in this audience, I don't need to say very much about why we study dark energy and modified gravity model. I just say that we are on a quest for a competitive model that explains late-time acceleration. And I guess a good place where to start is GR. I mean, from the fact that GR is an excellent description of what goes on at a vast range of scales and corresponding, I guess, cosmological epochs as well. We can start from it, and we can pretty much, we know that GR is the unique theory, the unique consistent low energy theory, Lorentz invariant of a massless spin 2 particle, and to it we can add additional ingredients in a simple way, and we're doing just add a scalar, just like we do for inflation. We can, of course, choose to be more radical and modify the theory more fundamentally, in the sense that we can consider Lorentz breaking theory, we can consider a massive spin 2 as opposed to a massless one. There's many things that we can do, and in the quest for this mechanism for late-time acceleration. And of course, what I want to say here is that most of them come with extra fields, extra degrees of freedom, and it better be, for the reason that I said before about GR, that in the appropriate environment, these degrees of freedom are screened. Now, this is not always the case, but in most cases it's true. So there are, of course, interesting exceptions, such as Lorentz violating massive gravity, for example. But I'm going to assume here, in what follows, that we need to be able to screen, and I'm going to look at LSS probes in the case in which screening is there, and it's important. All right, so let me just take a scalar as an example, just because it's easier. If I write down a generic Lagrangian of this extra field, we need to screen it, and there are several ways to screen it. We can look at it phenomenologically. To this additional scalar, there is an associated fifth force. The corresponding potential is here. As you can see, it goes like 1 over r. So in principle, it can be very strong, generate a 1 over r squared force in direct competition with GR. So it better be that in the appropriate environments, this fifth force is screened. We can do it in several ways. We can have, depending on the environment, low density versus high density, for example. We can ask that the coupling itself, G here, is configuration dependent, or we can ask that the mass is very large whenever we want to screen, or we can screen kinetically. In this case, we'll be using zeta, in other words, the kinetic term, and this falls into the category of Weinstein screening. So what I'm going to say can be applied to all screening mechanisms, but as I provide more and more details, we're going to focus on Weinstein screen theories in what follows. All right, so the starting plot for our analysis is this one, and I want to draw your attention to the fact that this plot and this plot are supposed to be the same. So later on, I'm going to refer to this one as if these two are the same. So please use imagination. I know this is a very crappy way of drawing it. So this is a plot which was obtained by Falk and collaborators in 2015. And this is what basically inspired our work. So let me explain this plot a little bit. What you see here on the y-axis is the fractional difference of the dark matter power spectrum in DGP and in lambda CDM. Now, DGP here serves as a proxy for Galileans, massive gravity, etc., not just DGP. And this is important to keep in mind. And there's a plot as a function of k. You see 3 colors there, and they represent 3 different regions of the DGP, Galilean, massive gravity, parameter space. OK, so blue, red, and black. And here, I guess it's blue, red, and white. So let's just take a look. Now, the 0 horizontal line corresponds to no difference with respect to lambda CDM. So there is a region parameter space in, let's say, Galilean theories or DGP, where there's no difference absolutely from the get-go. Here you see the line is basically horizontal, so the signal is the same as the one in lambda CDM. Now we know by construction that here we're talking about DGP, so there's an additional degree of freedom. So the obvious interpretation is that screening is so strong from the very beginning in terms of k that we see nothing about it. This extra field in this setup is not there. Screening is very, very strong. Happens immediately at linear scales, right here. On the other hand, if we probe other regions of the parameter space, the red one, for example, we see that there's a 10% difference at linear scales, and as we go towards quasi-linear scales, screening kicks in, and eventually we go down to the lambda CDM signal. Of course, things can be different, And there's a continuum, of course, of possibilities here. They just plotted 3 of those. We can have an even bigger difference at linear scales. And only later on, much later on, at highly nonlinear scales, screening kicks in, and we go down to 0. Now, this has been done with embodied simulations. But what we tried to do with Zmony was to provide an analytical description of this same phenomena. And of course, we tried to do this in the case in which we stopped. We stopped our description at quasi-linear scales, because that's where we have access to by using perturbative or assisted perturbative methods. And I'll clarify what I mean by this assisted or resound perturbation theory. Before that, let me just give you a status of what's going on within these perturbative approaches to large-scale structure. Now, there's a lot of work in this direction by several groups. And I think so far it's a relatively successful story, so it's very interesting what's going on. So first of all, at linear scales, perturbation theory works very well. We all know that, so there's nothing to say about it. At highly nonlinear scale, of course, perturbation theory fails. I mean, you can think of it as an expansion in, let's say, k over k nonlinear parameter. When k over k nonlinear approaches 1, perturbation theory is bound to fail. It fails, and we have to resort to numerical simulation. So no one is trying to do perturbation theory here, of course. The effort is all in this sweet spot in between the two, which is called the quasi-linear scales, mildly nonlinear scales, whatever you prefer. And here, there's several competing approaches to the problem here to describe the dynamics. You can pick your favorite acronym there from RPT, TRG, TSPT, Lagrangian, IPhT of LSS. Many people in the audience actually have worked on this and are working on this. The effort is focused on basically extending the k-reach of perturbation theory. And the simple reason is that the number of modes that we can control, the information basically, grows like k cubed. So it's very important if we have a perturbative description that it's true up to here, to push the boundary of what's allowed within perturbation theory. So this is what's going on. And our analysis fits very well within this framework. But you might ask, we have seen the initial plot, right? Here we're going to very large k, which perturbation theory will never be able to do. So why even bother? Why do we even have to look at perturbation theory as a tool to describe LSS dynamics? So the answer, I guess, is we can argue about all of these points, but I listed the points that to me are more important. So the first point is basically a matter of taste. I think if we have to truly understand the physical principle that underlie the data that we are about to collect, it is preferable to have an analytical description of what's going on to pair up with simulation. But this is semi-philosophical reason. Another one is that, as you have seen last week and this week, there is this effort to write down an effective field theory of dark energy, so a perturbative description in model space. And this would fit very well in order to create a map of what's going on in terms of perturbative framework in large-scale structure. You can actually do clear-cut map between this dark energy modified gravity model space and the perturbative or effective theory description of large-scale structure. Now, the other reason, which is very dear to me, is actually the role of symmetries in this setup. In particular, I have in mind consistency conditions or consistency relations. Now, you might be more familiar with consistency relations in the context, in inflationary context. There you know that, or even more in general, and these are just a consequence of word identities. But for example, that the consistency relation are relations between n+1 point function, the squeeze limit, or if you want the soft limit of n+1 point function, and their endpoint counterpart. They're very important. They are the result of residual symmetries in the description of your physical system, but they have observational consequences. They do have those for inflation. They do have those for large-scale structure. The very reason why we say that a detection of FNL higher than a certain threshold is actually almost a smoking gun for multi-field or other multi-clock inflationary models is entirely due to consistency relations. Basically, when a consistency relation is in place, the squeeze limit, for example, of the bispectrum leading term can be interpreted as a transformation being applied on the power spectrum, so it's a gauge artifact. So what we actually observe is a sub-leading term when consistency relations are in place. If they are not in place, on the other hand, the signal gets enhanced. And this is true for the inflationary context. It's also true in the Lasker structure context. In fact, one interesting information is that the symmetries which are the heart of consistency relation during inflation are the very same symmetries, in particular the non-relativistic limit, are the symmetries which play a key role during in large-scale structure dynamics. And to make a long story short, in order to make sense of consistency relations, they're being in play or they're being broken, it's of course ideal to have a perturbative description of what's going on.
Matteo, just a comment.
Yeah.
What you are saying refers to local.
Yes, squeezed. Yes, absolutely. Yes, yes, yes. I mean, the same reason it's not true for a finite equilateral and so on and so forth. Absolutely. And the other reason, more practical, if you will, is that in this perturbative approach, it's relatively easy, or it's easier at least, to include several layers of physics. And by that I mean initial conditions and so on and so forth. In fact, here I'm listing some of these additional layers within this EFT over LSS approach, but I must say that the same is true for all these perturbative approaches. So you can include non-Gaussianity, bias traces, baryons, etc. And actually with Zorni, we focused on talking about clustering, quintessence, and screening. And this is true for this EFT over LSS approach. And there is our work by, I think, Baumann et al. But this is also true for all the other approaches. I mean, this is true of all perturbation theory frameworks. I think actually Diego and Sergei did the same thing with their approach. This is general feature of perturbative approaches. It's quite, it lends itself nicely to us, including several years of physics. I want you to talk about two different models, but I will focus on a model with screening. So this clustering quintessence, I'm not going to say too much about this model. It's a very interesting model on its own. A lot of people worked on it, including people in the audience. Perhaps I would just say two things. The first one, well, here you see there's a model with just dark matter, and there's the clustering quintessence component. You take the limit in which CS goes to 0, so dark matter and clustering quintessence have the same speed. This simplifies the analysis a lot. In fact, there's a nice trick by Sefosati and Vernizzi that effectively reduces the system to solving the problem with just 1 degree of freedom. And this is very nice because your expansion parameter is just 1. It's the typical K over KNL. And you can do a lot. You can go a long way towards solving this system. In fact, with Zorni, we solved that to all orders in perturbation theory. And we provided integral and differential solutions. So because of this nice variable, nice simplification that it was pointed out, the solution was on only to quadratic order, and we did it to all orders. Now this model can actually be embedded, for example, within this EFT of LSS. Perhaps Matt will have to say something about this afternoon, but this is all I'm going to say about this model. I want to focus on a model with screening. And here I'm going to be quite schematic because I want convey the idea, not the details, but we can talk about the details later. So the model I'm considering here is, you can think of it as a Galilean-like model. So we have dark matter plus Galilean. They are coupled at least gravitationally. And we have the very own equation of motion for the Galilean. Now, the physical point that I want to make is that whilst when we were talking about just dark matter or even clustering quintessence, there is just one expansion parameter, K over KNL. There's going to be another scale here in the problem, which comes straight from the Galilean sector, or the Galilean-like sector. This scale, I'm going to call it KV, and correspondingly, there is an expansion parameter, which I'm going to call K over KV, which is crucial in the problem. Now, KV is there and to signal when nonlinearities in the Galilean sector become important. I've not even written them down here. I will later. But KV is the scale at which nonlinearities in the Galilean sector become important. In other words, when screening becomes important, when screening becomes effective. That's their role. Now, there are, of course, KV and KNL are not completely independent, but they can be very, very different. In fact, there can be a very wide hierarchy between these two scales. And let me just briefly consider all the possibilities. Now, let's say that this KV is very, very small. This means that K over KV itself is, for every K of interest, is very large. Screening kicks in immediately. So there's immediate screening, even at linear scales. And this basically corresponds to what we see in embodied simulations in the blue line. Right? There's immediate screening. For all intents and purposes, the signal looks like lambda CDM. And that's true when KV is very, very small. the opposite direction. At the other end of the spectrum, there is a situation in which KV is much larger than KNL. This means that if this is a good expansion parameter, this is an even better expansion parameter. So we can just do perturbation theory, be very happy, and there's no problem. The perturbation theory works out very well. You can just solve your system. It might be hard, but it can be done. You have full perturbative control up until whenever K over KNL starts being too large. But K over KV is even smaller, so there is no problem whatsoever. Now, the interesting case for us is this one. So whenever KV is actually smaller than KNL. Why is that? Well, that's because as we go to higher and higher K, we are still at what we would normally call quasi-linear scales, in the sense that K over KNL is completely under control. It's a small quantity. But since KV is smaller than KNL, we're going to hit a region where screening on the Galilean sector becomes very important, and yet we might as well be at quasi-linear scales as far as dark matter is concerned. And this is, again, sort of what's going on here. On the other hand, here, as you know, it's the other end of the spectrum. So this is what we're interested in, this setup. And I'm not going to say too much about what KV is. Of course, I'm not going to go through the details. If you think, instead of thinking about KV, you might be more comfortable thinking about the Weinstein radius. So being in the region for K much larger than KV basically corresponds to being inside the Weinstein radius, and K much smaller than KV corresponds to being outside the Weinstein radius. Now, because of what we know about the Weinstein radius, we know that KV, for example, is time-dependent, because whenever we solve a system and find out what is the functional form of the Weinstein radius, what makes up the Weinstein radius, we know that there is some dependence on the source, the Schwarzschild radius. We know that there is dependence on the background. So this Weinstein radius set therefore KV is time dependent. And we know that there is also a dependence on some universal quantity, which is there in your Lagrangian right away. For example, here written down the equation of motion for the cubic Galilean, and lambda cubed, of course, is going to make up your definition of the Weinstein radius, and it's going to make up your definition of KV as well. But this slide is just to say that whenever you think of KV, it immediately corresponds to the Weinstein radius. Now, equipped with this, with this mindset, what one can do, presented with the system of equations that we saw before, is just solve the system, which is great and ideal, and nothing else needs to be said about it, except that this is very hard. It has been done under simplifying assumptions. So if you assume spherical symmetry, if you assume the quasi-static approximation, for example, this system can be solved, and this is a very worthwhile endeavor by itself. But what we wanted to do was to actually sort of give up on solving the system exactly for the sake of solving the system in a more generic situation with time dependence and without spherical symmetry, without this sort of symmetries. Now remember that we're interested in the situation in which KV is much smaller or smaller than KNL. What does it mean? Well, it means that eventually the perturbative result is not going to be enough, because although this is a good expansion parameter, this is not anymore. We're probably in regions in which this is a good expansion parameter and this is not. So in that case, the perturbative solution is not enough to describe our system. So instead of, let me actually write down here, just write down here for reference that we have control over P perturbative, and we want to describe the situation in which perturbation theory is not enough to describe the system. And I'm going to write down P perturbative as P lambda CDM later on plus P perturbative minus P lambda CDM. And I'm going to call this delta P. And it will become clear later why this is useful. But basically, whenever we need to resum the expansion in K over KV, in general, what we can do is just take our perturbative result here and apply to it a kernel, which takes care of the resummation. Now, if you're familiar with what's going on with this BAO within the perturbative framework, you will immediately be reminded of this formula, which has been used to make sense of the so-called BAO resummation scheme. This has been done in several different approaches. It works out in all of them. And the burden of describing what's going on with the BAO is taken up by the kernels there. Of course, the dynamics is quite different. What we're trying to describe in our case is screening, but formally, You can immediately do the connection with what's going on in that situation. Now, there, in order to derive the kernel, one can do it from first principle or sort of first principle. You can use Lagrangian perturbation theory to get the form of these kernels. In our case, we're being phenomenological, so instead of deriving them from first principle, we're going to apply some guiding principle to determine the form of these kernels. And remember, for us, these kernels, their function is to take care of screening whenever perturbation theory is not enough to do so because K over KV is quite large. That's what we use them for. There are some criteria to find them, and let's use them. So first of all, this resummed power spectrum can be written down in several different forms, but we're going to write it down basically this way that I wrote down for you. Since we know the asymptotic of it, since we know that eventually at high K, we're going to go towards lambda CDM, it is convenient to apply the kernel just to delta P, not to P. Because again, for K much larger than KV, screening kicks in. So this term must be suppressed. So the kernels must be suppressing this part of the signal. On the other hand, for K much smaller than KV, perturbation theory works out very well. So there is no need for these kernels, and these kernels must reduce to 1. Just with this couple of conditions, the immediate guess of how a kernel might look like is that it might be Gaussian, it might be Lorentzian. I mean, there are not so many possibilities, but these are two obvious ones. And the fact that you see only even powers of K there is just basically rotational invariance. So there's no, rotational invariance is enough to dictate the K-square dependence. The other criteria, which it's a bit more technical, so there's not a lot of time to get into it, but we call it no double counting. And what we mean by that is that as you go higher and higher in perturbation theory, part of the screening, although inefficiently, is going to be described by the perturbative contribution, and part of the screening is going to be described by the kernel. So we need to be careful not to double count the screening, and that's where this no double counting criteria comes from. And because of this criteria, and the details of it are in the paper, because of this criteria, it turns out that the Gaussian kernel is by far preferable to this, what we call the Lorentzian kernel. It's just a matter of these alphas are in principle arbitrary coefficients. They are there to take into account the fact that KV is actually really time dependent. Remember what I've said before. And remember the fact that here there is an integral. And the fact that we're being phenomenological is clear also from the fact that here we're not really implementing any integration. We are still considering the kernel to be time dependent, and the time dependence is going to be eaten up by these alphas. But because of this no double counting criteria, it turns out that the Gaussian kernels are by far preferable to the Lorentzian kernels. So actually, I'm almost done. What I want to show here is a plot. And again, here I'm plotting the fractional difference of the dark matter power spectrum between a fully screened system and lambda CDM. And you might have this in mind whenever you're looking at that picture. Of course, this is not the same picture. Remember, this one was obtained by embodied simulations of, Galilean-like degrees of freedom. Here, there's quite a lot of assumption that went into doing this, simplifying assumption. So it would not be fair to compare that one with this one. In fact, we normalized it differently just to make this point very clear. Because of all I've said so far, in order to compare our framework with the result of embodied simulations, we would need the exact expression for p-perturbative. Remember, this is our starting point. We assume that we have p-perturbative at our disposal, and then we can compare with what people have done with embodied simulations. We do not have those. We do not have those at the time. So what we did was to consider a number of additional assumptions, and because of that, we were basically able to plot this fractional difference in the power spectra up to 2 loops. And because of our simplification, it turns out that what you see there is entirely due to our kernel. So every single behavior of this fractional difference is due to the kernels because everything else drops out. And of course, here we are fixing KV, although remember that KV is in principle time dependence, and that's taken up by the alphas in general. We're fixing KV. There's just one constant that needs to be one needs to choose the value of these constants. We go up to 2 loops, and you can see that depending on where KV is, screening kicks in at different scales. Also, the same behavior which can be observed with embodied simulation, we're able to mimic within our framework. And of course, what is with this framework at our disposal, there are 2 obvious things that we must do and we can do. The first one, I think I've already mentioned, at least partially, is that whenever one, well, I guess, is comfortable making a few simplifying assumptions like spherical symmetry and quasi-static approximation, there are solvable models. The system that I showed at the beginning can be solved exactly. And so it would be ideal for us to take a toy model, take a system that can be solved, and compare it with our kernels. How are our kernels doing? Are they describing everything that we see? I mean, the fact that we're able to mimic what's going on in the embodied simulation plot is, of course, very encouraging, but that's what we're going to do next. Have a model that we can solve exactly, and compare those kernels with our phenomenological kernel. This will tell us a lot more about our framework. And, of course, there's the comparison with simulations. Now, the last thing I want to say is that the physics of it is going to be exactly the same. The kernels might be slightly different, but we're working also on including other screening mechanisms within this framework. And I'm going to stop here.
So I guess, can you hear me? Is that hello? Okay.
Yeah.
I guess this. So right now, I mean, as far as I understand, really, essentially, you're just fitting. It's a fitting function, right? I mean, there's some
Well,
choice of.
There are choices.
You're choosing a particular set of things that you believe will be good, but right now it's a fitting function, and it will not be a fitting function if you can predict something about another set of parameters or something like that.
Let me
So, for example, I mean, have you tested how well you do if, say, I don't know, you fit your alphas to one case and then you change some parameters so KV has a different time dependence?
So
do the alphas stay the same?
In the same direction, but we're doing something different now. So what we want to do is, to fit. I wouldn't use the word fit, but I'll give it to you. Let's just say fit, because I mean, there's a lot of possible choices, and it turns out with this no double counting, you really have. But anyway, we actually want to do the same kind of apply the same reasoning to the bispectrum. And then if the same alphas are involved, and only the same alphas, then you can actually say something about the bispectrum, what you have in your hands for the power spectrum. And that's when you're being predictive. That's when you would say, we're not doing fitting function anymore. So our next step is to actually find an observable for which we fix alpha 1 and alpha 2, say, and then we go to the bispectrum, show that only alpha 1 and alpha 2 are involved in the same thing, and then see what we can say about the bispectrum. Of course, we will need to compare with simulation for the bispectrum, but this can be done. So this is the next step. Find another observable for which the same alphas and not more are involved.
Okay, so good. So that's one test. But on the other hand, if I were to simulate the model, I can get the bispectrum out of the simulation, right?
Yes,
so
yes.
in order to do those two, I mean, I get the bispectrum for free if I've done the simulation already.
Sure.
So somehow it seems to me more relevant that what happens is that your alphas remain unchanged. Or predictably changed as you change some parameters. So I think this seems like a more pertinent question, no?
Well, that's certainly another thing to do. Yeah. I mean, I have to reveal that now we're working on the bispectrum, but I mean, that's in our radar.
Yeah, I think on a similar note, like for the BAO, it was more clear that you could resum the effects because they were due to the linear displacement. So so you could compute exactly what that is because you can compute it in perturbation theory.
Yeah.
But here, it doesn't seem clear that there's even a hope of resumming because
I mean, hence
it's
the phenomenological,
due just
right?
to the nonlinear.
But that's why we say it's first of all, I mean, the fact that, as I said very clearly at the beginning, in that case, it's been derived with Lagrange perturbation theory. While here, what we can do, that's exactly here, right? We can consider a case in which we can solve exactly, and this has been done, and compare with our kernels. In that case, we can just see one on the left, one on the right, and compare. Now, if we could solve exactly a very complicated and more realistic models, then our approach would not be needed. So in a sense, we can only compare with the simple and then start trusting this approach more and more. So that's the idea. Yeah.
Okay, and sorry, just one more. Is this breakup between K nonlinear and KV? I mean, if the extra degree of freedom starts getting nonlinear, it's also going to induce nonlinearities in the dark matter field and change k nonlinear as well.
Yeah, so actually as k over kv gets stronger and stronger, that actually switches off the coupling between these two. So if kv was 0, then you would basically just see dark matter. So the direction is this one. K over kv gets bigger and bigger. The coupling between these two goes down. So you're killing the coupling.
So when kv becomes...
No, when k over kv becomes very large, that's when the coupling between these two goes down. And that's when you stop seeing the effect of these electrofields. So if you take kv to be very small, then any k would do.
Sorry, Matteo. So you show your at the beginning of your slide. So this platform simulations for NDGP. Yes. So in there, I mean, this KV thing was in the fully nonlinear regime, like really large K. But you need, at least for your plots you showed, they were at various much smaller Ks.
Yeah.
I'm just asking, is there any interesting model, viable, that you expect actually to see this? Because that's important, right?
Yes, that is the whole point, yes. So, I mean, within the, if we were to look at it from the DGP perspective, you know, what basically determines KV is the so-called crossover scale. And in this paper, they show that it, you know, because of previous analysis, it's a very meaningful part of the parameter space. And so we have done actually a back of the envelope calculation before doing these studies within massive gravity, in which we know that it corresponds to a reasonable value for m squared, bare m squared, as you know. Now, actually, what we're working on is actually into showing exactly that same parameter space corresponds to quasi-linear scales. We have the calculation that shows this, but the fact that values of m squared is a good value comes actually from other analysis, you know, cosmological analysis, nothing to do with LSS, you know, the fact that we want a region where there is no Gucci, no gradient, et cetera, et cetera. So yeah, so we have very much that in mind. We want a proper, if we're talking about massive gravity, we know that this area, screening kicking in at quasi-linear scales, there are models in which this corresponds to a good, healthy value for m squared. And we checked this. I mean, we didn't do the full
So for
thing.
massive gravity, at least, I mean, you expect such a thing happen.
Yes.
Okay, that's great. Okay.
Yes.
Thank you.
Good. So what exactly is KV?
Well, so KV stands, it's there, it's a placeholder for where the...
You should be able to estimate it, right, as a function.
Yeah, I mean, it's, let's say that, I mean, it depends a lot on the parameters of the theory. Let's say that, you know, it's a meaningful value could be 0.1 inverse megaparsec, fine. But
no, but it's, I mean, I think, so what you want to, the Weinstein argument you gave was for spherically symmetric
I know.
So for what you want to do here is do the equivalent in momentum space.
Yes.
Given delta, so get delta sources of phi, and then you ask at what scale it becomes nonlinear.
Yeah,
so
and of course, it's also going to be a series dependent on the background, and the time depends on the background as well. So I mean, for now, this KV it just stands there for where screening kicks in.
Okay, but then you should work it out.
Yeah,
right?
yeah.